Welcome to VisualLearn AI, the ultimate fast track to success. In just 2 months, we'll help you unlock your potential one test at a time. With a PhD crafted curriculum, every lesson is designed for excellence. Now let's dive in and solve today's challenge together. So this question is from the 2024 Physics 1 free response question. It is a conservation of energy question, and it consists of a block of mass m rolling down a track with two loops. It follows the path that I'm showing here in red. The high point of the first loop is B, and the high point of the second loop is C. The heights are given over here. So first of all, we start by writing down the equation that's provided in the formula sheet for the potential energy. So the potential energy will be equal to mass times gravity times the difference in height delta H. And to set up the problem, we will see that at point A, we have the potential energy as mg times 6r, which is the height at that point. And since the velocity is zero, because the mass m is initially at rest, the kinetic energy will also be zero. And at point B, we can also calculate the potential energy. Since that it is at a height of 2r, we'll have the potential energy at B equal to mg2r. Now, we don't know the kinetic energy at B at this point. However, we can calculate that using a physics principle, the physics principle of conservation of energy, that the energy at A will be equal to the energy at B if no work is done and no external forces are applied. So let's write down the physics principle here because it's important to do so in the free response question. So at point B, the rest of the energy is converted into kinetic energy due to the physics principle of conservation of energy. Okay, and we will also note here that no work is done on the system and no external force is applied to the system. So based off of this, we know that the total potential energy plus kinetic energy at point A was mg6r, and we know that the potential energy at point B was mg2r. So we can say that the kinetic energy at B will be the total energy plus the potential energy at B. And then just to write this down, the total energy was mg6r minus mg2r. Now that will give us the total kinetic energy of mg4r. So now we have the kinetic energy and potential energies at both point A and B, and our problem is well set up for us to go to the next step, which is to solve the first part of the question. Now this may look intimidating, but it's actually not that bad. So initially they're showing a shaded region in the diagram, and we have the potential energy and the kinetic energy is zero at point A. So in point B, we have to write down what the potential and kinetic energies are going to be. So based off of our setup, let's go ahead and copy what we wrote down. So we have at point A, the potential energy of mg6r and the kinetic energy of zero. So that shows up well in the graph that was provided to us. And then now write down what we calculated. We have the potential energy of B equal to mg2r and the kinetic energy that we calculated to be mg4r. Now, obviously, both the energies are conserved at point A and B, so we can make this bar chart. So U would be mg2r and kb would be mg4r. And that would solve part A. Now part B talks about starting with the conservation of energy. So they give us the physics principle and they want us to derive an expression for the speed of the block at point B. So express your answer in terms of r and begin your derivation with writing a fundamental physics principle. So we start off by writing the physics principle here, and we want to be explicit about that. So the physics principle is the conservation of energy since no work is done on the system. All right, and then the other part of this is that the energy at A will be equal to the energy at B. So we write down the energy of A as mg6r plus 0, which is the kinetic energy, and then mg2r. And this time, instead of using the mg4r that we calculated, let's use half mv squared, which is the kinetic energy. And the reason we're doing is that we have to put in a variable v so that we can calculate it. So by doing that and moving mg2r to the other side, isolating half mv squared, we get mg4r equal to mv squared by 2. So the masses will just cancel out and add the 2 there, and then v squared becomes 8 times gr, or we can also write in terms of v square root v equal to square root of 8 times gr. So that solves that. That will give us the value of v. So we derived the speed of the block at point B using this equation. Now let's move on to part C. Part C is going to get a little bit tricky. And on the following dot, draw the label of components at point C. So now we're moving over to the third loop. So in the third loop of point C, now there's an interesting thing here. We have to make sure that we follow how the mass M is moving. So the mass M is going to be towards the inside of the track. So now usually the normal force is upwards. In this case, we'll have first of all the weight mg acting vertically downwards, but the normal force will also be acting in that direction because the mass M is on the inner loop, the inside of the loop. Had it been on the outside of the loop, the normal force would point in the other direction. So now we have mg and we have n in this direction. Okay, now this is a little bit more tricky. A student claims that 4r is the minimum height at point A such that the block can slide through point C without losing contact with the track. So briefly explain why this claim is incorrect. All right, so again, first of all, we have to start off with the physics principle. We have to be explicit in what we write down. We'll have to go ahead and derive this. So what the physics principle is that in order to remain in contact with the track, the centripetal force, so now we're talking about the centripetal force, must exist to keep the block on the loop. Okay, so that's important to write it down explicitly and to mention the centripetal force. Now, the formula for the centripetal force is half mv squared over r. All right, now what is the centripetal force composed of? It is actually mg and n that are added to it. Now we write down mg plus n equal to mv squared over r. Okay, there's one more thing here though. We have another condition. The condition is that the block can slide through point C without losing contact with the track. So when is this going to be true? So what is the minimum condition for the block to keep in contact? So the minimum condition will be that if n is equal to 0. Obviously n can have a force, but in this case we're looking at the condition for n equal to 0. So if n is equal to 0, we have simply mg equal to mv squared over r, and then we can get rid of the m's, and we're left with v squared equal to gr or V equal to square root of GR. Okay, now that is our velocity condition, which is the minimum condition to remain on the track. But we're not done yet. We have to actually find the height, the minimum height at A that corresponds to that. Now we're going to have to check the student's claim. So the student is saying that the minimum height that it can be released from is 4r. So how do we check that? So we use, again, the physics principle. So the physics principle has to be explicitly called out here again, and that is the conservation of energy. So this principle will say that the energy at A will be equal to the energy at C. We've done the same thing with energy of A and energy of B, but now it's time to do the comparison with the point C, the third loop. So in this loop, we'll just go ahead and say that energy at A equal to mg times h. Now, h is the minimum unknown value of height. And we're not going to say it's 4r. We're going to say, okay, we're going to find out if that h comes out to be 4r. And now we're going to go ahead and write down mgh equal to writing down the energy of C, which will again be the potential energy plus the kinetic energy. So mg2r plus half mv squared. And then the V is going to be the V that we just calculated, V squared equal to GR. Now substituting it back in. Now this will be simplified because the mg's are going to cancel out. Once the mg's are canceled out, we quickly get that h equal to 2r plus half r, so that's 2.5r. All right, so this is not equal to 4. Instead, that h is equal to 2.5r. So we've actually went ahead and solved this problem, but let's go ahead and explicitly write it down on why the student's claims are incorrect. So we say that hence the student's claims are incorrect because the block needs to be released at h equal to 2.5 r to have enough energy to maintain contact with the track. All right, now all the parts of this question are solved. Let's just do a very quick recap of this problem. Going back to the first step, we went ahead and calculated all of the potential and kinetic energies. We were able to set up our problem. Even without the velocity, we were able to calculate the kinetic energy and then draw the graphs based off of that. And then we derived, using the conservation of energy, the velocity at B. And then finally, we drew the forces diagram and eventually found out the value of V